Hey guys, Mr. Palmer back with part two of this second thermodynamics problem. This one, we just found the Kp in the last part. It asks us to take that value, right, and we're going to do something to find the delta G here, right? We're told that this Kp value is 124. The equation we're going to need to do this relationship is given to you on your equation sheet. Delta G is equal to negative T Rnk. R T ln K. We're looking for delta G, negative. Which R value you're going to use? Really important. The R value you're using is the one for joules, 8.3145 times 298 Kelvin. That's our T value. That's what was given to us in the problem. And then we're going to put in natural log of K, and our Kp, it says, is 124, right? We have a K value larger than 1, you're going to wind up with a negative value for delta G. That gives you negative 1194 joules, right? Remember, this is in joules. Doesn't ask you for kilojoules, but you could write it that way too, 1.194 kilojoules in that problem. I'd say, that might be 1 point, maybe 2 points if they're making sure that you have the correct sign on it. That might be important as well. E says, based on your calculation in part D and the information provided, calculate the entropy change. Well, what did we do here? In part D, we calculated our enthalpy change, or rather our free energy change. So our free energy change, which we had in the last one, was negative 1.194 kilojoules, right? What do we know about the delta H? Well, the delta H, if I go all the way back, I'm not using the delta H that I got calculated in this part right here. The delta H I'm using is the delta H for our reaction right here, per mole of reaction, the negative 23.44. So let's get back to where we are. Negative 23.44 minus T delta S. Well, what's our T? Our T is 298 times delta S, and we're going to solve for delta S. So let's solve this. We're going to bring this to the other side, right? Remember, this is 1.194 kilojoules. We got 23.44. We're subtracting a negative from both sides, so that's really adding a positive to this side. So we're going to come out with a positive number. Well, I'm doing this along with you. 23.44. It's going to give you 22.2, and that's going to be positive. I'm just going to put that on there. Kilojoules equals negative 298 times our delta S value. Now, we're going to be dividing by a negative, so we're going to wind up getting a negative number. I divide by 298, and that's going to give me 0.0747 kilojoules per Kelvin. Or you could write this, and that's going to be a negative. Again, we're dividing by a negative. Negative 74.7 joules per Kelvin. Delta S is typically given in joules per Kelvin. That's pretty straightforward as a plug and chug. I'd probably say that's probably worth 2 points. One for using your correct value, substituting from the delta H information, and another for correctly putting in your delta G and solving. Let's take a look at the last part, and this one's just a Lewis part. This doesn't really have anything to do with thermodynamics, but you're going to expect that. And it's asked us to draw complete Lewis structures, carbon monoxide and carbon dioxide. Just to double check yourself, carbon monoxide, right? We've got carbon has 4, oxygen has 6. We've got 10 electrons. Our total need is 16. we have 10, which means you got to share 6 doing a need have share. Give everybody their octet, and we're going to be left with this structure. So this should be properly written C, triple bond O. There's only one way to put that together, and each gets a lone pair. Carbon dioxide, that's probably worth a point, is going to be CO2. And hopefully you guys know at this point that it's double bonded. Each of the oxygen has 2 lone pairs. If you count up the electrons, this has 4. Each of these have 6, right? So that's going to be 16 is what we have. The need is 8, and 8 is 32. If you subtract that, there's a sharing of 8. And of course, we do have a sharing of 8. So we've got this structure right here for the CO2, this structure for the carbon monoxide, and it says, based on your Lewis structure you drew, explain why carbon monoxide is a polar molecule and CO2 is nonpolar. Well, looking at our diagram, remember oxygen has a higher electronegativity. This is a polar bond, right? This side, oxygen, right, has a higher electronegativity. It makes this side slightly negative. This side of the molecule slightly positive. However, in carbon dioxide, because this is a linear molecule, the oxygens are going to pull equal and opposite, and we're not going to get a polar molecule. We're not going to get a dipole out of this because they're pulling equal and opposite, having to do with the shape. I would say it's probably 1 point for each of these, and probably 1 point for an explanation that involves the fact that this has a symmetry and it has a linear structure to it. Okay, see you guys on the next one.